Hello, this video will be short because it's kind of an interlude to the other stuff we're doing. But the point here is that I already said a few times that non-renormalizable theories can be really useful in certain conditions, right? Despite this apparent problem with the infinite amount of renormalization conditions, right? We know that there are many important physics results that were obtained with non-renormalizable theories, right? And I want to give you, for now, right, this provisory intuition on how can that be, what are the conditions in which you can actually use non-renormalizable theories, right? I won't prove big theorems on this video, because we will understand much better the relation between even renormalizable and non-renormalizable theories once we go into a new approach to renormalization. Another one, an alternative to the one with counterterms we're doing so far, right? But there's a lot we can already see with the approach we are using, and that's what we're doing for this video. Now, I want to use a concrete example, right? So I will actually use a non-renormalizable interaction that was really powerful to understand weak interactions at the time people were formulating the standard model, which is Fermi interaction that involves 4 fermions. So this thing right here. I already mentioned this interaction in the previous video, and don't worry about this combination of gamma matrices here. It can be many different things depending on the current, right? People used to call these terms current, right, that you use, but they are not important for us because we're mostly doing dimensional analysis here, and the specific form of these matrices does not matter to us, right? So now if you think of a particular 4-point function, right, in this theory, it will look like this, right? So you have this 1pi kernel here, right? This core of the vertex of the n-point function, right? And you have fermion propagators going in and out, right? Keep in mind that this is an amputated 1pi function, so these guys are really not the propagators, but more like just a reminder how many external points I'm considering here, right? I won't do the dashed every time because it can be bothersome, but and then the first contribution to this will be given by a simple 3-level vertex, right? Which is proportional to the Fermi coupling constant, right? The next contribution is where the loops start to appear, and then renormalization becomes important. So you have a loop that looks like this. Now we'll talk about fermions, so I have to give a direction, right? And you have these external lines which are amputated. And they also have a direction here. And of course you have other terms, right? You have this loop. This is very similar to lambda phi 4 actually, right? You have a loop in the T channel, in the U channel, depending on of course, the flavors of the fermions. You can complicate this a lot. We want to focus on the spirit of the thing, right? We know from the superficial divergence criteria that this guy diverges, right? And now, of course, if I want to renormalize this theory, right? If I call this initial coupling constant G0f, now I can define a GF, a physical GF, and get counter terms. So I can get a term that looks like this, delta GF, right, times the same operator, right? And with appropriate renormalization conditions, I can make the contributions from the counter term cancel the divergences here and define a particular measurable coupling constant, right, Fermi constant, which at some particular reference point in energy I can measure. So far so good. It appears that we have a 4-point function which I can renormalize with one condition, and that's fine, right? But let's look at the 6-point function, right? So this interaction, this very same 4 fermion interaction right here, will generate a contribution to the 6-point function, right? That looks like this. Let me try to draw it, right? So I have three of those vertices, right? The external legs will be like this. Let me give them directions, so I can put 2 of them, 3 of them going in, 3 out. That does not matter too much as long as I don't violate any number conservation. Okay. And then I can connect them like this. And you can easily see that this is just at every point the 4 fermion interaction that we had at the start, right? And again, just by doing dimensional analysis here, you can see that this diverges too, right? This is also a divergent diagram, and the integral of this loop has a different form from the integral of this one, so it won't be eliminated by the same counter term at all. I mean, this is not the case of a nested or divergent subdiagram like I mentioned before. This is a genuinely new diverging diagram, right? In order to renormalize this one, right, I have to go back to my Lagrangian, right, and put a new term there. The only term that can potentially solve these 6-point function divergence is something that looks like, let's call this GF prime, right? Fermi never really proposed this interaction, but just because it's very similar to that one, right? I put a 0 here because this is the before renormalization, and now I need a new term that looks like that. I need an extra pair of fermions, right? Because this guy now I can redefine to get GF prime, that will be the physical interaction with 6 fermions, right? Plus some counter term. Let's call that delta GF prime. And this counter term I can now use a condition that does the cancellation for these divergence, right? If you don't think too much about it, you can still manage, right? You think, well, every time I want to calculate a new n-point function, I will need a new condition. But as long as I'm not calculating all the n-point functions, still a finite quantity. But that's not true, right? And the reason is this new interaction that I put here, right, also contributes to the 4-point function, right? So if I go back, let me copy this. If I go back now to that series there, which is the 4-point function expansion, I can draw a new diagram here now. Let me put it right here, right? Which is very similar to this one. So remember, this first vertex here is proportional to GF, right? But in the second one too. But now there's a new diagram that looks like this. This is a closed line here, right? And this vertex now is proportional to GF prime, right? So now, and there's more, right? And you go on. So now you see, even to calculate the 4-point function, I need to first renormalize the 6-point function, because I need to know the value for this guy, right? And there are also eliminate the divergences that appear for the 6-point function. So you see now the problem, right? Because I did that between the 4 and the 6, right? But I could have done the 8, I could have done the 10, I could have done the 12. All of them will have new, each step in that tower of problems, right? I have a new kind of divergence that needs a new condition, and I can pretty much make any of these new interactions that I have to introduce, right? The next step would be to put a 8 fermion interaction, right? I can, any of these interactions influences basically every other endpoint function, right? So you see that even for the calculation of one simple 4-point function, I might need an infinite amount of parameters, right? You can think that as parameters, you can think that as the renormalization conditions if you're really theoretical, or you can think that as measurements. To really fix my theory, I need to do an infinite amount of measurements to know all these coefficients, and that's really not a predictive theory, right? And then you could ask, right? So how did the 4 fermion interaction work, right? How did people understand weak interactions using such a broken theory? And the thing is, there are specific situations in which this can work, right? And again, dimensional analysis is our friend here and allows us to see how that could work. So the first thing is to realize that the dimension of these couplings that I'm creating here is decreasing as I go to higher and higher dimensional operators. So if I take the original Fermi constant, and let's call it GF4, to remember there's 4 fermion interaction, and then I can call this thing I call GF prime, GF6, and GF prime prime, which I didn't define, but I would call GF8, and so on, right? I can go all the way to an infinite amount of different couplings, right? But the trend is consistent, right? So if you look at the dimension of this product of 2 fermions, right? So the dimension of psi bar psi and the matrix in the middle that has no dimensions, right? This is in 4 dimensions. This is dimension 3, right? Because each fermion field has dimension 3/2, which we have shown in the previous video, right? So every time I put another bilinear, fermion bilinear like that, I'm increasing the dimension of the operator by 3, and that means I decrease the dimension of the coupling constant also by 3, right? And since in 4 dimensions, right, the original the Lagrangian, any term in the Lagrangian needs to have dimension 4, right? It means that the original Fermi constant, which I call GF4 here, has dimension -2, right? Because with 2 bilinears, the total dimension of the operator is 6. So this guy needs to have dimension -2 to get a total dimension of 4. And then every next step decreases this by 3. So GF6 has dimension -5. GF8 has dimension -8, right? And so on. Right. Now, dimensionful quantities, right? They introduced scales in your theory, right? This is a natural scale for your theory, essentially, right? There's a number. with dimension of 1 over energy squared. So I can rewrite these couplings in a more intuitive way by extracting the dimension out of them, right? I could write GF4 as G4 times some mass scale to the power -2, which I'll call M4. And I could do that for the others, right? So this is for 6. G6, M6, in this case is the power of -5. And for 8, G8 here, to the power of -8, right? But I want to simplify stuff a little bit. I don't need these many scales, right? So let's assume that these are all the same scale. Let's just call that M. This is not important for my argument, right? Because I'm soon making the assumption that these are all very high energy scales. And so if I'm just making them really high, it doesn't matter if they are the same or not, just that they are all really high compared to the experiment I'm using this theory in, right? I'm trying to describe some experiment, and as long as these scales are much higher than the scale in which I'm doing the experiment, I don't care if they are the same or not, right? And again, by doing that, I have all these G and are now adimensional quantities. They're just pure numbers, right? And I'm keeping the dimensions in this scale, right? Now, if I want to look at a 4-point function, right, and do some dimensional analysis, you can go back to the LSZ formalism and do dimensional analysis there. You see that the dimension of a matrix element of a 2-to-2 scattering, and that means a 4-point function, right, is 0, right? That means the dimension of the module of M squared is also 0. Why? And that's specific for 4-point functions, right? You can do dimensional analysis for other n-point functions, and the dimensions will be different, right? Why is that important? This is important because then I can estimate how these guys, how they scale with the external momentum, right? So if I take M, the module of M222 square, right? This will receive contributions from all these operators, as I said, right? I can always draw something, take GF6, right? I can always draw a diagram that looks like this and contributes to the 2-to-2 scattering through a 6-point fermion interaction. Same for 8, same for 10, right? I can go nuts here, right? But for in each case, take the 4-point function. This will be proportional, of course, to G4 square, right? And 1 over M to the 4th. But now I know that this thing needs to be adimensional, right? So that there needs to be something in the numerator here that compensates for the dimension of M4, right? And the only dimensionful quantities that I have in this calculation are really the external momenta, right? Which at the lowest bound can be equal to the masses of the particles, right? But they can be anything but in, and the point is, okay, I'll put external momenta here. Let's assume they are all of a similar scale. So I have to put a p to the 4 here. I'll represent, say, in this case I have 4 momenta. I'll just assume this. Some p, right? So p represents the scale in which I'm doing this experiment, right? I'll have many contributions. Between them, that contribution that comes from the 6 fermion interaction, which will look like G6 square, right? M to the 10, right? Because this goes linear in M. So when I take M square, I have to take the square of that. And now, of course, to make this a dimensional, I have to put P to the 10 here. And so on, right? When I get to G8 square, I have even higher powers of P square, right? So you can see, right, now where our hope comes from, right? If I'm doing my experiment at a scale characterized by this guy, which is much smaller than this characteristic scale of the theory, right, then I can, even within these contributions of one endpoint function to all the others, I can ignore all these contributions from the higher dimensional operators. There will be a finite number of higher dimensional operators, the non-renormalizable interactions, that contribute, right? But not all of them, right? At least there's a finite number that contributes at a level that is bigger than your experimental uncertainty, right? All the others will be hidden inside the uncertainty of your experiment. They are basically impossible to see, right? So in that situation where you have some scale for your theory and you're working far below that scale, renormalizable theories are perfectly fine, right? They only a finite number of operators will contribute. You can find experimentally the size of these physical couplings. So that's what happened for the Fermi constant. We know the number, right? And that fixes and you explain everything with just that term. Even if you know there are others, right? They are just, their contribution is just too small, right? In the case of the Fermi interaction, right, that natural scale was the mass of the W and the Z boson. Right? So while you were below, far below those masses, you were doing fine, and Fermi interaction with just that 4 fermion interaction was perfectly good to describe your phenomenology, right? The experiments you were looking at. The same is true for chiral perturbation theory, right? You managed to describe a lot of the hadronic interactions using a non-renormalizable theory, right, of pions. So those were good, right? Now, this could be conceived as, wow, we are really lucky, right? And for a while people were wondering about that, because now you have, I just made 3 types of theory, right? The renormalizable ones, the non-renormalizable that have a particular scale that is high, and the non-renormalizable theories that have a low scale. And in that case, you're lost, right? In the third type, right? And people at some point in the story of quantum field theory, people were really wondering why we kept finding physical systems at high energy that were either renormalizable or had no renormalizable descriptions, which had really high scales, so they worked. And it was not clear why we were so lucky as to always have theories with this scale high, or even just renormalizable theories, right? We'll see further ahead in the course that actually this is not lucky at all. This is the natural state of affairs, right? But it's hard to see that immediately just using these kind of renormalization we're doing. Once we get to what was called a Wilsonian renormalization approach, then we'll see that this is quite natural. This is how you expect theories to behave, right? But that's a subject for the next videos. So for now, that's all. Thank you.